All right, guys, we're going to take a look at example number 2, which is going to give us 2 new graphs to work with. And we'll once again examine what kind of three-dimensional solids we can construct from the area that we have enclosed. And we'll take a look at some of the shapes we've already seen, and we'll also see some new structural setups. So here we have y equals x squared plus 2, so a parabola. And then we have y equals x plus 2, so just a line. So if we go to graph our line, we're going to go up 2, and then we're going up 1 and over 1. So let's go ahead and connect those points. Then we have our parabola. So our parabola is also going to have a y-intercept at 2. And then if we think about setting these two equations equal to one another in order to solve for their intersection points, what we can do is we'll subtract the 2's away, so those will cancel. We'll have x squared equals x. So I want to subtract over that x like this, and then I'll have x is times 1 minus x is equal to 0. So our intersection points here are just 0 and 1. So my parabola is going to be right here, so intersecting there at 1. So I have that tiny enclosed region. And it asks me first to figure out the volume when I have cross-sectional areas that are squares. So that looks more like a rectangle than a square, but what I have is these shapes coming off my page like this. So let me see if I can do any kind of better visualization. This region is the shape that we're looking at here. And so you can imagine this is the base of the square. And then if you can give yourself a three-dimensional square piece that comes off, you can imagine if you have infinitely many of these, kind of the three-dimensional structure that's going to result. Hopefully that 3D online visualizer gives you a little bit better picture here, but you can kind of imagine it's going to arch down this way and then get smaller and smaller. I'm not certain that that was helpful at all, but hopefully your graphs are useful to you in the way that mine's may be useful to me. But otherwise, I think that GeoGebra link gives a really good kind of picture of what our three-dimensional volumes look like. So once again, a square is just going to be something that we can find the area of using the side length squared. And so in this case, our side length value would come from looking at our upper function and subtracting off our lower function. So in this case, for the graph that we have here, that would simply be x plus 2, that quantity, minus x squared plus 2, that quantity there. So the good news is that this 2 here and this 2 here would cancel one another out. And so if I just want to consider the area of the enclosed region, it's simply going to be described by x minus x squared. So that would just be the regular area. But we are interested in going from regular area of the graph to a three-dimensional volume because we're treating a length along the graph like the side of a square. So what I can do is square that component, and that's going to get me from area to volume because I'm introducing a new dimension. So simply my area is just a one-dimensional piece, so I'm integrating one dimension, and then I integrate from 2 dimensions to get to my volume in 3 dimensions. My integration bounds here would go from 0 to 1 because my intersection points of the graph go from 0 to 1. So that's my volume integral here. And again, if you wanted to keep it fully separate so you could see the setup without eliminating the 2's, you could certainly do that as well. Then let's go ahead and take a look at part B. This one says, find the volume of the solid, so same solid as before, but this time where your cross-sectional areas are rectangles with a height of 3. So let me give myself a bigger looking picture than I did before. So I'm just going to make my spacing a little bit bigger. So that way I can try to better draw out what we have. So there is my parabola. And then my line is going to look like this. So I still have that smaller enclosed region here. This piece right here. But now, instead of having squares, it tells me my cross-sectional areas are rectangles of height 3. So I have my base, but then my height is given by 3. So this is one of my rectangles coming out of the page. This is another rectangle, and another rectangle, and you can kind of see that as more and more contribute, these rectangles all should have the same height, but they're changing because their width is affected by what is going on with the function at that point in time. So that's going to be my three-dimensional structure of interest, that kind of enclosed piece right there. So a rectangle, that area you can find just by multiplying your length times your width, or your base times your height. And so we can define our width as the area in between the upper and the lower function. And then our width is just, or I'm sorry, our height is just going to be what they give us, this value of 3. So we can go ahead and set up our volume by multiplying by 3 out in front. We're going from our lower bound to our upper bound as far as our intersection goes. And then our width value is just going to be that x, our upper line, which is x plus 2. And then we're going to be subtracting off x squared plus 2. So once again, we can simplify that if we want to cancel those 2's out, and this would instead become the integral from 0 to 1, and then we have x minus x squared integrating with respect to x. So you'll notice that there's no volume, there's no squared piece there to get to the volume, and the reason for that is we have the dimension here of our length and our width, and then the third dimension comes from integrating over that area. So that is our volume set up here, this 3 times the integral from 0 to 1 of x minus x squared. Finally, we have one more shape that we can encounter, and this is going to be a volume that's constructed from using an isosceles right triangle. So a triangle that has 2 equal sides and then 1 longer hypotenuse. So once more, I'll sketch out the same graphs that I had above. So our line and our parabola. So give myself my line segment right here. And then our parabola is right here. So in this case, if we're trying to sketch in the shape, the hypotenuse is right along the graph that we're working with. But then we have this right triangle that's coming up off of the graph, and that's going to give it that 3-dimensional structure. So the hypotenuse is the side that's along the graph, and the 2 shorter sides are the ones that are coming off in a 3-dimensional structural setup. So what you want to do in this case is consider, okay, if I have a hypotenuse and I have 2 sides in a right triangle that are equal because it's isosceles, I'm going to have an x here and an x here, and then this is my hypotenuse. So I need to think about how I solve for the area in an isosceles right triangle, and then also how I can use that information to relate back to the hypotenuse, which is the side length that I have information about. So an area of a right triangle like this can be found by multiplying x by x, that's just your base times your height, which is the same thing as saying x squared. Now the Pythagorean theorem is going to give me some useful information here, because the way I can relate x and h is by saying x squared, or a squared, plus x squared, or b squared, is equal to my hypotenuse squared, or c squared. So this would then become 2x squared is equal to my hypotenuse squared, and then I can divide both sides by 2. So I know that x squared is equal to my hypotenuse squared over 2. I also know that my area is equal to x squared. So my area can also be written as my hypotenuse squared divided by 2, which then allows me to set up this integral in terms of the hypotenuse, which is a length that I know. So if we want to do that, we can say our volume is equal to, our integration bounds are going to go from 0 to 1, and our hypotenuse is the same setup we've been working with all along. So x plus 2 minus x squared plus 2. That quantity is squared, and then we are dividing that by 2 and integrating with respect to x. Again, if you want to cancel those 2's out, this is going to go from 0 to 1. I can pull a 1/2 out in front if I just wanted to deal with the constant after integrating. And then inside, I would end up with x minus x squared, that quantity squared, integrating with respect to x. And that would be my final result right there. Now that's it as far as your new notes for today. And let me give you a quick rundown on what you want to look out for your homework. So your homework tonight is going to come from 3 different places. You just have 3 problems from your textbook. So each of those problems is going to give you the same function, but then some different shapes for the cross-sectional areas. So they're multi-part. Then you have a Khan Academy practice page for known cross-sections. So again, that's going to be a square, a semicircle, a triangle, something like that. And then you have this supplemental worksheet that's linked here. This is specifically, if I can open this up for you, this is a series of multiple choice problems from the AP exam. And so what I would like you to try are problems 1 through 6. That's going to be this first problem and the second problem and the third problem. And so see if you can visualize what cross-section is being constructed and then where you might have an upper function and a lower function as far as seeing what the area is, because that will give you your radius, or it will give you your side length, or it'll give you your hypotenuse. So on Monday, we will have a review day of this content. So that way you can ask any questions that you have. We can go over the homeworks together and we can make sure you're feeling confident with this material. And then our official review day will be on Tuesday. And then our multiple choice will be on Wednesday and our free response will be on Thursday. So that's our plan coming up. Please let me know if you have any questions and I'm happy to answer those via email. Thank you guys.